Every single day, millions of us step into elevators without a second thought. We just trust them. But behind that simple act of faith, there's a whole world of incredible engineering keeping us safe. Today, we're going to pull back the curtain on one very specific and pretty fascinating piece of that puzzle. I mean, really think about it. You push a button and you put your complete trust in this machine to lift you, dozens, maybe even hundreds of feet into the air. It's just a fundamental part of modern life, this little act of collective faith that we all perform constantly. And that right there, that is the core question. Because in some of the most common, most efficient elevator designs, the very thing pushing you skyward is this long, totally unsupported steel column. So what invisible forces are trying to bend it? And what kind of brilliant engineering is stopping them? Well, that's exactly what we're going to dive into. So let's start with the technology right at the heart of this whole story. The guideless hydraulic jack. It's an amazing piece of equipment for saving space in a building. But that efficiency? It comes with a very specific and very critical engineering challenge. So what is this thing? Well, a telescopic jack is kind of like a collapsible telescope. It extends out in stages to lift the elevator way up high, but then it collapses into a much smaller, compact space when the car's at the bottom. And for architects and builders, this is a huge deal. It's all about maximizing usable floor space. But here's where things get interesting. A standard jack is usually braced by guide rails along the wall. Think of it like a rock climber using handholds. It's stable. But a guideless jack? Nope. It stands completely free. It's more like a flagpole in the wind, and it has to absorb every single side-to-side force all by itself. You know, an analysis from Novin Puya Elevator puts it really clearly. The jack itself becomes the one and only line of defense against any sideways force. If that thing bends, the whole system is in trouble. This is the core engineering problem that absolutely has to be solved. Okay, so the crucial next step is to figure out what is actually trying to bend the jack in the first place. And we're not talking about obvious forces here. These are subtle, almost invisible stresses that engineers have to see coming and plan for. The analysis basically breaks it down into four main culprits. You've got something called eccentric loading. We'll get to that in a sec. Then there's initial misalignment, which can be tiny imperfections from the installation. You also have dynamic forces, from the car starting and stopping. And believe it or not, even the friction between moving parts plays a role. But the biggest and most common threat of them all is eccentric loading. Here's how to think about it. Imagine everyone in a crowded elevator suddenly decides to huddle in one corner. That tiny shift in the car's center of gravity creates an off-center load. And that acts like a giant lever, putting a surprisingly powerful bending force on that long steel jack way down below. So knowing what the threats are is one thing, but predicting their exact impact, that's a whole other ballgame. This is where the math becomes absolutely critical. Engineers can't just cross their fingers and hope for the best. They have to calculate the absolute breaking point to make sure the jack never, ever even gets close to it. And get this, they don't calculate for an average day or a typical load. No way. They run the numbers for the absolute ultimate stress test, the elevator at its highest possible point, where the jack is stretched out to its max and most vulnerable, and it's packed with the maximum weight it's rated for. The thinking is, if it's safe under those conditions, it's safe under all conditions. To make sure it's safe, engineers follow this super methodical 5-step process. First, they figure out the maximum possible side force. That's our eccentric load. Then they calculate what's called the bending moment, which is basically how that side force tries to twist the jack. Third, they calculate the actual stress this puts on steel. Then, step 4, and this one is a biggie, they analyze the buckling load. That's the absolute limit before the column could suddenly fail. And finally, they plug all those numbers into a special safety formula to double-check that the design is well within a safe range. And this is exactly why step 4 is so important. Buckling isn't just a slow bend. It's a catastrophic, sudden collapse. Just picture pressing down on a plastic ruler from both ends. It holds, it holds, it holds, and then bam, it snaps outward. For a guideless jack, that is the most likely and the most dangerous way it can fail. So preventing buckling, that's priority number 1. So how in the world do you actually build something that can stand up to all this invisible stress? We've picked apart the problem, so now let's look at the solutions, the engineering blueprint for a jack that is designed to simply refuse to fail. It really boils down to 4 key things. You can make the piston walls thicker, you can use higher grade, stronger steel, You can make sure the installation is absolutely perfect to get rid of any initial stress. But the most powerful tool in the engineer's toolbox is the diameter of the piston itself. And this, right here, is where the engineering gets really clever. The relationship isn't linear, it's not one-to-one. Doubling the diameter doesn't just double the strength. Because of the way the physics works, even a small increase in the piston's diameter leads to a massive exponential increase in its ability to resist buckling. It is the single most effective safety feature you can build in. All right, let's zoom out and bring this all together. We've gone deep into bending moments and buckling loads, but what does it all really mean for us? Well, it means that the simple trust we put in an elevator every day isn't just blind faith, it's a trust in this very specific, very deep expertise. Because, let's be honest, the stakes could not be any higher. If these calculations are off, if the design is flawed, the consequences are severe. We're talking permanent damage to the equipment, hydraulic leaks, and all the way up to a complete system failure that puts passenger safety at risk. This isn't just about making things work efficiently, it's about safety, pure and simple. The Novenpoya analysis really concludes with the most important point of all. Safety in these kinds of complex systems is never, ever an accident. It is earned. It's earned through meticulous calculation, through strict standards, and an absolute commitment to getting the engineering right every single time. So the big takeaway here is that behind every smooth, quiet elevator ride, there's a world of hidden calculations and smart design choices. It's really a testament to the engineers who solve these complex problems so the rest of us never even have to think about them. That simple act of trust is really backed by a profound understanding of physics, materials, and force. And now, you're in on the secret.